We all know that our future is digital, and that's also industry. Indeed, nowadays we are already used to take digital impressions, and for that a plethora of digital cameras and scanners is available, and this number is growing quickly. For some of the systems we have the possibility to do the 3D modeling and milling chairside. One of the most known and studied systems that has the possibility to make those one-day restorations is the Xerox system. You have to prepare the tools, make an optical impression, do the 3D modeling, and mill the restoration out of a CAD-CAM block, and then go to the restoration to the tool. Research into and production of materials suitable for CAD-CAM restorations is one of the fastest growing and changing fields in dental materials. Most CAD-CAM blocks that are used for fabrication of indirect bonded two-tone restorations are made out of glass ceramics. We have feldspar, lucite reinforced, and lithium silicate glass ceramics. These materials, they are strong, they have superior optical properties. However, these are stiff materials, brittle, with low fracture toughness, and a high susceptibility to fracture, as you can see here on these detailed pictures. To overcome the shortcomings of glass ceramics, the so-called hybrid ceramics have recently been introduced to the market. We have resin nanoceramics, polymer infiltrated ceramics, and also the GC company has quite recently introduced a hybrid ceramic CAD-CAM block made out of flexible nanoceramics. It's called the Cira Smart Block. This material consists of ultra-fine homogeneously dispersed fillers, as you can see on these transmission electron microscopic pictures. The material is highly cured without residual stress. Therefore, this material is claimed to offer optimal flexibility, fast and precise milling, sharp margin of adaptation, easy polishing, staining and glazing, and this in combination with optimal aesthetics. What are now our findings regarding the Cira Smart hybrid CAD-CAM block? I will present first some of our laboratory data and next our clinical experience. In the first in vitro study, the influence of different surface treatments on the microtensile bond strength of the Cira Smart hybrid block was evaluated. We have different surface treatments, phosphoric acid etching, sandblasting with 30 micron aluminum oxide powder, and etching with 5% hydrofluoric acid. Eventually followed by application of silane and or application of an unfilled resin. For luting, we used or a dual cure luting composite or a light cure flowable composite. Here we have the scanning electron microscopic pictures of the different surface treatments. They show that micromechanical interlocking is created by sandblasting and by hydrofluoric acid etching, and this seems to be quite important to have a good bond with the Cira Smart. Indeed, the conclusions of this in vitro study were that surface treatment that enhances micromechanical interlocking either by sandblasting or hydrofluoric acid etching is mandatory to significantly increase the bond strength. Phosphoric acid etching and ceramization did not improve bond strength. Next, application of the unfilled resin as an extra step is not necessary. And finally, a flowable light cure composite can be used as an alternative to a dual cure luting cement. Then in the second in vitro study, the mini fracture toughness of different CAD-CAM blocks was evaluated. Here we have a schematical presentation of the study setup. A 4-point bending test was done on these little small bars that were built out of the different CAD-CAM blocks. Here we have the results, and then you can see that the mini fracture toughness for the Cira Smart block was significantly higher than for the zirconium lithium silicate glass ceramics and for the feldspar ceramic. In vivo, we used the Cira Smart blocks for fabrication of unlaced partial crowns, as you can see here. Also for the fabrication of endo crowns. It's actually a material that fills the indication gap between an extended direct composite restoration, and a conventional crown. It's also a material that's useful for treatment of mineralized toothware because of its high flexibility and high wear resistance. Compared with glass ceramics, the following differences were observed. More fast milling and more precise milling, resulting in a better marginal adaptation for the Sierra Smart restoration, as you can see here on this first molar at the conical side. For the polishing procedure, you can do the mechanical polishing with rubber polishing point very fast. It takes about 3 minutes. And also the glazing and staining procedure with the OptiGlaze system is easier and less time-consuming compared with glazing and staining of glass ceramic restoration. While the aesthetic result for both restorations during the dry-in phase with the neutral dry-in phase is quite similar. Finally, regarding surface treatment before cementation, it's easier. It consists in the first step of sandblasting with aluminum oxide powder, followed by application of silane, and finally here in this case an unfilled resin was applied. It was air-tinned because in this case we used solely light durable restorative composite for cementation, and with the unfilled resin we had an optimal wetting of the inner surface of the restoration. Here the excess of cement is removed and then light curing takes place for 40 seconds each surface. This is the result after cementation. Another advantage of the Sierra Smart restorations is that they are easily repairable with composite. So this easy repair procedure can lengthen the lifespan of these restorations. So these sort of findings, our findings with the Sierra Smart hybrid block are positive. But of course, we are interested in the clinical performance of these different types of restorations after long-term clinical functioning. Hereby I would like to thank you.